Hello everyone, my name is Lauren Barnes and I'm a PhD student at New Jersey Institute of Technology working with Dr. Anand Oza, and today I'll be talking about resonance, instability, and dynamical stabilization in bouncing droplet chains. So I'll start by describing the problem. So we have a fluid bath being vertically vibrated with forcing acceleration gamma, and because of this forcing, a small drop can actually bounce or walk on the surface of the bath without coalescing with the fluid. And we're going to consider a regime of gamma in which it's below the Faraday instability threshold, gamma F. So basically this means that the surface remains flat unless perturbed. So when the droplet bounces, it perturbs the surface and excites standing waves or Faraday waves on the surface. And the drop actually interacts with its own wave field that it produces, because when it deflects off of its wave field, since it's not flat, it propels the drop so that it moves in the XY plane. So in this way, it self-propels itself. And the waves decay over time, but how fast they decay depends on the memory parameter, also known as the forcing acceleration gamma. We call it the memory parameter because for high gamma, or high memory, we have the waves staying around for longer, and for lower gamma, they decay more quickly. And this system is interesting because it exhibits some quantum phenomena, and yet it is a macroscopic problem. So it's interesting in that regard. And if we have a one-dimensional chain of 5 droplets, so let's say lined up along the x-axis, then we have this governing system of equations here. And the parameters kappa and beta depend on gamma, the memory parameter, forcing acceleration of the bath. So in this way, this system does in fact depend on gamma. And we consider equilibrium states of 5 droplets bouncing at fixed positions, so not moving, just bouncing in place. So to that end, we plug the ansatz, considering no time dependence, into the trajectory equation on the previous page, and we obtain this system of 5 equations and 5 unknowns. And then if we define these interdrop distances, so d1 is the distance between drops 1 and 2, d2 is the distance between drops 2 and 3, and if we consider a symmetric chain, so that's an assumption where D1 is equal to D4 and D2 equals D3, then we get this system of just 2 equations and 2 unknowns. And if we plot the level curves of these functions, their intersections correspond to equilibrium configurations for the drops. And we did a linear stability analysis on these for the lowest gamma considered, which is 0.66, we see that we have both stable and unstable solutions. So the blue dots represent stable and the red are unstable. And we are going to mostly focus on this N11 bouncing state, but also really on all 4 of the blue bouncing states, the stable ones. And we see that from our linear stability analysis, we see that these blue dots, the stable states, go unstable to an oscillatory instability as gamma is increased. So we also look at this case where we force the droplet on one end, so sinusoidally, and we prescribe this amplitude A1 and frequency F, so we'll call that drop 1 on one end of the chain. And then because of the particle wave interactions with these droplets, the droplets not only interact with their own waves, but also with the waves produced by their neighbors. So therefore, forcing the first drop has an effect on all the other drops as well. And of course, this also depends on the memory parameter gamma and also the initial configuration that we choose. So basically one of the equilibrium states. And then here are some results from simulations that we ran. So for each gamma A1 pairing, we can see that there's a certain resonant frequency F at which drop 1 can be forced, for which we get maximal oscillation amplitude of the other 4 drops in the chain, 4 unforced drops. And in fact, for the highest value of gamma that we consider, so 0.74, we see that the amplitudes of the other drops' oscillations actually can exceed that of the imposed forcing on drop 1, which basically shows that these drops are extracting energy from the wave field. And another interesting result we notice here is that as the forcing frequency F on drop 1 goes to infinity, we have the amplitudes of the other drops' oscillations approaching 0. So in other words, it's like the chain is approaching another bouncing state, no oscillations. So in this high F limit, we have this new bouncing state effectively being dynamically stabilized by that rapid forcing being applied to the first drop. And then to verify this, we just plugged in that steady state ansatz for drops 2 through 5 into the trajectory equation, and then took the limit as f goes to infinity, and we obtained this system of equations, which we solved using numerical continuation in the parameter a1, which again is the forcing amplitude imposed on drop 1. So then panel A of this figure shows the interdrop distances initialized at the N11 bouncing state. So that black square in panel A corresponds to the N11 bouncing state. And panel B, we can see the wave profile, that's the blue curve, and the black dots represent the drops for the N11 equilibrium bouncing state. So that's where we initialize it. And then we see that there, the interdrop distances are all roughly similar to each other. But then as we increase the forcing amplitude on drop 1, we see that the distance d1 gets large. So basically drop 1 gets further and further away from the chain. And then we see that d1 plateaus at that gray horizontal dashed line. That gray square corresponds to another equilibrium state, but an unstable equilibrium state. So you can see that in panel C. That's the wave profile and the drops for the unstable equilibrium state. And then that gray dashed line in figure A, that is the distance d1 between drops 1 and 2 for that unstable equilibrium state in panel C. So we see that d1 for panel A plateaus at that value. So basically what's happening here is that unstable equilibrium state is being dynamically stabilized by the rapid forcing on the first drop. And then that's panel D shows that. So that shows what the wave profile looks like for that case, with drop 1 being forced. So that's a very interesting result. Another interesting result that we get is for higher memory and larger amplitude imposed on drop 1, the trajectories no longer just oscillate in a bounded oscillatory state anymore. Instead, they start to jump around chaotically. And panel B shows us the cycle averaged interdrop distances. So in other words, we average over one cycle of the drop 1 forcing for each of those times. And these horizontal dashed lines here correspond to the interdrop spacing for the N11, N22, and N33 stable bouncing equilibrium states. So we see that here for this forced droplet case, we have these interdrop distances kind of jumping between these stable states, but not settling near any of them, or not settling down. They keep jumping around chaotically. So in conclusion, we see that these equilibrium configurations of 5 drops go unstable to an oscillatory instability as gamma is increased. And then also we get a complex dynamics when we force the drop on one end of the chain. And to that end, in the high frequency limit of that forcing, the unstable bouncing states may be dynamically stabilized. And last but not least, at largest forcing amplitude and memory considered, the periodic forcing can actually generate a chaotic dynamics. So some interesting results there, and thank you so much for listening.